Yeah. So these were the cutoffs just from Samik's website. So from this, you can kind of infer that the problems were somewhat hard. Actually, I think this is like the year that was famous for having P2 being the convex Hull track problem. So, but you didn't even need that to qualify because you needed like 27 for it. Okay. So the first problem is called parchment. The second problem is called weightage. So I'm going to be covering parchment and Samik is going to be covering weightage. Before we start, I think it would be important to point out that on weightage, I think one of the subtasks here is bugged, and because of that, you can only get like I think 63 points and not 100 unless you do some weird stuff. I'm not actually sure which one it is, but I know that one of them has its input format wrong. So if you have tried to AC this and failed, that could be the reason. Okay, so anyway, I'm gonna do parchment. So I'll begin by just summarizing the problem. Basically, everyone's following, right? I can start. Everyone's good with that. Okay. Yeah, on P2 the subtask is bugged, so it's kind of weird to get 100. You can't get it with a straightforward solution. That's actually why I don't have AC on this problem either, actually. I have AC on this one though. Okay, anyway, so you have an array. Okay. Each number is like from 1 to 10 raised to 6. And it's of size n, and you can basically choose a range x to x plus k, and you can delete all of the numbers that are in this range. You can do this as many times as you want. Now you're also given another array called f, and like let's not think of this as an array actually. Let's just think of this as multiple queries. So one value of f denotes that you can perform this operation like at max f times, and you basically need to find the minimum value of k such that in less than or equal to f operations you can delete every element in the array. If you guys want, although I'm sure everyone over here has probably read the problem before, but if you want, you can still take time to read it now, or you can ask questions if you didn't understand the problem now. Or you can confirm that you did by just saying yes in chat or something. Okay? Okay, so I'm gonna take that as no one has questions, and one person has understood the problem. Uh, okay. Anyway, so full solve for this is pretty interesting, but I'm going to start with the subtasks. So, firstly, we have subtask 1 for 3 points. A is equal to 1. What is A again? A is the maximum value in the array. So, basically, your array is going to be like a number of ones, right? Because you have this. So, it could be like 1. Oh, it could be like 1, or it could be 1, 1, 1. Basically, notice that the number of ones actually doesn't matter because this operation is going to delete it anyway. So, you're going to have an identical array in all cases. So, any guesses as to what the solution for this will be? 3 points. You just have one element that you need to delete. That's all. It's going to be one operation, exactly. I think it's always possible too because your value of k is also going to be 0, right? Because you just need to delete x. So it's just going to be, I think you can just print 1 and you'll be done. So you already secured 3 points. How much percent is that of 27? 3 by 27. Yeah, you're 11% the way to clearing ZCO just by printing 1, which I think is pretty cool. Okay. Now the next subtask is f is equal to 1. Okay, what is f again? F is the number of operations that you can perform. So when f is equal to 1, that means that I can only perform one operation. So if I can only perform one operation, and I want to delete every element in the array, what is the... You need to minimize k. Yes, you do need to minimize k while staying under the number of operations, yeah. K should be the maximum difference, yeah, exactly, because you need to cover from min to max, you just have one operation, so it's going to be like, let's say you had an array like 1 comma 2, then k would also have to just be like 2 minus, gonna be 2 minus 1, right? Because it's gonna be 1 to 1 plus 1. So k is just gonna be max minus min. So with that, if everyone understood this, you're gonna get 4 more points. That is, let's just do the max cutoff again. You're now, oh my god, wow, 25% of the way, 26% of the way to clearing ZCO. Alright. So now you may be thinking, okay, this is pretty easy. So you may want to, like, let's see what the next subtask is. Okay, it's f less than or equal to 2. Now we have two operations. Okay. Any ideas for this one? Yeah, if it's 1, so we basically just have 2, yeah. And you divide the difference into 2. Uh, can you explain what you mean by this exactly? Okay, so you're kind of right. Basically, when you have two operations, you're just going to choose like one point in the middle. Like, I can actually draw this out if you guys want. But for that, I'll need to stop sharing my screen, so I'd rather do it here. Okay. So let's say that this is an entire interval. Okay. And this is the min element, which I'll denote with small m, and this is the max element, which I'll denote with capital M. So if you have exactly one operation, of course, your one operation is just going to be this, right? And now if you have two operations, it could be like something like this and something like this, right? It could be. But we could also just transform that solution to be something like this. So my point is that there is a valid solution with you having like the first point, leftmost point at small m, the middle point at some number, we don't know that yet. Let's call that number x, right? So this is going to be small m, this is going to be x, this is going to be x plus 1, and this is going to be capital M. So now the solution is actually to just loop over all possible values of x, of which there are O of a values, right? So for k is equal to, is it called k? No, for f is equal to 2, this would be the solution. Hope that makes sense. Guys, this is worth 6 more points. So it's double the weight of, so this would get you 20% closer, so it should make sense. Yeah, this is the third subtask, yeah. I don't understand how you get the middle number. You never get it, you loop over all possibilities for it. And then you can just do the operation. I think it may even be easier than that. It's fine, this is a pretty easy subtask anyway, so. Okay. I'm gonna do the same thing again. By the way, if you're like a girl, or if you're in lower grades, this is even higher. So now you're 50% of the way there. Let's say you were in 10th grade. Uh, you'd be 65% of the way there. Let's say you were a class 7 girl. How many points did we get so far? 3 plus 4 plus 6. Yeah, you'd have already cleared the cutoff. Okay. Now we move on to some of the more interesting subtasks. So we have stuff like this, where we need to actually think of a solution that is like more than just special cases. So what I'm going to do is I'm just going to discuss all of these together because I think the solution is like very similar for all of them. Okay. This is ZCO can easily be qualified by problem 2. Problem 2 is also actually very nice, but I like this problem a lot, P1. Because it uses a really cool trick towards the end. Okay. So, now for this subtask, we actually need to do stuff. So, now I want you guys to think about what the simplest possible thing we could do to solve this would be. If I were to just give you some kind of solution, so there are some keywords over here that mean, there's not really keywords as you might be used to the term in like board exams or whatever, but there are like hints towards the approach that you may need to use. So like for example, something like you have at most f times and they're asking minimum power level. So that like hints towards something very particular, which actually has been covered here a lot as well. Okay, we have DP or binary search. Binary search, yeah, it's binary search exactly, and a lot of people got that, which is a good sign, right? So now, why would like when would binary search work? Binary search would work when we can calculate the number of times, right, using some kind of function, and we fix some other parameter. In this case, that parameter will be k. Since we want to minimize k, we are going to binary search to find like a valid value of k such that we can perform the operation f times. So for this, we need to fix k, right? That's the first step. Hopefully that makes sense. Like, you guys are understanding what I am saying, right? By when I said we need to fix k. Maybe there'll be, maybe it would be unclear, so please like ask if it is. So k is the mid. Okay, thank you for asking. So basically what I mean is, let's not think of the problem in terms of like some random number k. Let's actually assign a value to k. So let's say that k is like 5. So then I have an interval from x to x plus 5, and I want to devise an optimal strategy in this case. That's what I'm trying to say. Okay, so I'm gonna think that I already know the value of k. And I want to think, suppose we knew that, then because the entire question is actually asking you to find the value of k under a constraint of the total operations being less than f, which is a bit harder. So I'm saying, let's say you didn't have any of that and you just had a definitive value of k that you need to use. Then what would you do? Okay, so do you guys understand now, or should I still clarify? Maybe if I give an example, it would actually be better. Example. Okay. So let's take a random array, like let's take like 1, 4, 10, and 16. Okay. So now I'm gonna take k is equal to 4. Okay. So if k is equal to 4 and I have this array, what do you guys think the optimal strategy would be to like delete this whole array? By optimal here, I mean a strategy which would use the least amount of moves. So now this is a really cool technique you can use in general as well, but sometimes you're just like forced to do certain operations. Over here, if you notice, whatever we end up doing in our optimal solution, we are going to have to, because our solution is taking an interval and going ahead, we have to start the interval over here at some point. So this has to be one of the moves. So now if we start it here, of course our thing is going to be starting at 1 and ending at 1 plus k. So it's going to be till 5. Right. Mm. Yeah. This makes sense, right? Why that has to be one of the operations. Yep. So that means we get rid of all of these, which is great. And now some people would think, okay, let's just do an operation from like, I don't know, 6 to 10. In this case, that actually works. So you know what? Let me just make it so it doesn't work, just to illustrate this point. Uh, for that, let's make k is equal to 3. I think that would be better. Yeah. Okay, so with k is equal to 3, this works, right? We get 1 to 4. And now let's say I just like covered it with another interval and I was like, okay, now next thing is going to be 5 to 8. Right? So do we see how this interval is actually like completely useless because it didn't delete any numbers, right? So we don't want it. But what can we actually do to get a useful interval? So clearly we don't want this. So I'm not gonna have this. Uh but what I wanna do is, again, now I've gotten rid of all of these, so you can actually kind of see it as we have a new array which just has 10 and 16. And if you remember what we did in the previous case is we just looked at the minimum element and started an interval there, right? So actually we are gonna just do the same thing over here. And hopefully it makes sense why as well. or like why it's motivated to think to do like that. So next interval is gonna start at 10 and it's gonna go up to like 13. So it's not gonna cover this, but that's fine. So we have 10 to 13, right? That's the second operation. Remember, this was not actually an operation. I removed it. I'm not doing this, right? I did this first one and I'm doing the second one. And now our third operation is just going to be 16 to 19. So the answer for like this array with k is equal to 3 is going to be 3 operations. So let's say f was equal to 5 or something. Uh, that would mean that k is equal to 3 would be a valid value. Now, okay, so hopefully firstly this is clear. Because if this is clear, then we can start proving some stuff. I mean, not proving, but we can start showing some stuff that builds up on this. Hmm. Yeah, actually, in this case, you can make k1 as well because there are only 4 elements. So for f equals 5, it would work. But alright, wait, you can make k0. My bad, because that would just delete each element individually. But I just wanted to give this as an example. Suppose f was 3, then k is equal to 3 is the optimal. Okay, so does this make sense to everyone? I want to see like, yes, if you understood it, because and no if you haven't, because I want to like clear it out if you haven't understood it. I'm not sure if I was able to explain it well enough. I'll draw a line here too, since it's like the two. Oh wait, no, I don't need to draw a line here. I need to draw a line here. Yeah. Okay, so everyone understood it. Like, was there any part that was unclear? Well, this makes perfect sense. I'm talking especially not about just understanding the solution, but understanding like why we started over here and why we didn't start at like 5 but we went to 10 directly. That's everything is understood. Yeah, going to 5 was unnecessary. That's why we didn't, and that's why we went to the next smallest element remaining. That's what I'm saying. Okay, again, I'm just gonna take it as everyone understood, which is hopefully the case. Uh, so now how many points will this get you? Let's say I didn't want to think anymore and I just wanted to code this with binary search. Oh wait, I haven't explained why binary search is relevant yet. Okay, right, that's the next thing we're gonna do. Okay, so now when I'm claiming binary search will work, there's like something important that I need to like either prove or like convince myself of, and that is that if I decrease the value of k, like if k becomes smaller, right, what is going to happen to my answer? And answer over here refers to like the orange thing. What is going to happen to my answer? How many total segments we need to cover it if I decrease k? Well, one thing is for sure that like if we had a smaller k, we could always take a solution with that smaller k and just like use that exact same solution on a bigger value of k, and we would have the same answer, right? So this says that something particular is happening when I decrease k. So when I decrease k, I can only ever get more segments. I hope that is clear. It's not like more or equal. Like it's never going to it's never gonna go like this. It's only gonna look like that. Or actually like this because it's decreasing. Does that make sense? Because once you see this, the entire problem becomes pretty easy. And if you have solved some binary search sums before, so does this make sense? Hmm. Okay, like I can give you an example as well, just so uh it's more clear. Let's say, which color should I use for? Okay, let's use red for k is equal to 2. Okay, just as an example. So if I were to take k is equal to 2, then my intervals would be 1 to 3, right? So in fact, this 4 doesn't even get covered. So then my next interval would have to be 4 to 7. Again, like I'm just picking out single elements because my interval is too small, but my next interval would be 10 to 14. No, not 10 to 14. So this would be 4 to 6, I guess, not 4 to 7. Yeah, this would be 10 to 12. And this would be 16 to 18. Yeah, so in this case, you can see we have 1, 2, 3, 4 intervals. Before, we had 1, 2, and 3 intervals, right? So you can see it's clearly only ever increasing. I'll just remove this just to avoid some confusion. Yeah. So hopefully it makes sense what I just said. Yeah, in this case at k equals 0, it would be max number of operations. That's correct. But this makes sense, right? Like maybe maybe the next thought is, why do we even need to prove this? Or this was a very obvious statement that you spent like 5 minutes trying to show. What was the point of this? Right? I'm sure some people have that question. Because it's a pretty obvious statement, because like of course the bigger intervals we have, the more stuff we can cover. But what it lets you do is maybe not so obvious, because now we can picture this is a function, okay? Like over here we have the number of operations, and over here we have the value of k. So in the beginning, when k is equal to 0, of course we will have n operations, and as it goes on, it's going to continue decreasing. It's going to be in these step kind of ways, because we are dealing with discrete. And our entire goal is just to find a point, a value of k that's closest to the left. So like if it's here, it's better as compared to if it's here. We're gonna find some value of k. So I would actually draw it here just to be accurate, because it has to be to the leftmost, such that our number of operations is above some line over here. So like above below some number. So let's say this number is like x or something. I'm just putting numbers, or wait, they use a number in the question, right? I can just use the same one. Yeah, they used f, so I'm gonna use f. Okay. So the reason I drew this like this is, well, number one, the drawing looks pretty cool. That's my primary motivation. But my secondary motivation is like, doesn't this kind of look like a sorted array? Like if I were to draw a sorted array, like this is descendingly sorted, of course, but if I were to write a sorted array out and make the bars like the elements, it looks pretty similar, right? And let's say I wanted to find an element in a sorted array, then I would do binary search. That's the classical utility of binary search. So this is it's actually pretty similar what we are doing here as well. Okay, so does this part make sense? Is anyone confused about the graph I drew? Like for starters. Okay, wait. Instead of that, I should ask: does everyone understand the graph I drew? Does the graph I drew make sense? So if it does, just type yes. Yeah. X-axis represents the value of k. X-axis represents the value of k, and y-axis represents the number of operations. Represents the number of operations. Y is f and x is k. Yeah. Okay, so now that we're equipped with this knowledge, we can realize that we can do a binary search on this. And the way we do that is we choose one of these red bars. We start the red bar. Can I make my pen thicker? Okay, yeah. We start the red bar in the complete middle of the interval. Okay. Uh, Now we check. If we basically calculate the value of the function over here. So it's gonna come out to like this point. So if this point is below our orange line, that's good for us, and that means that we can go even more to the left. Suppose I had done it over here, just as an example, then my line would be uh, here, which is above the orange line. So that's very bad for us, because we're using more than f operations, right? And then each thing we can, like, suppose we have a range which we want to do, just check the midpoint, and in this midpoint, okay, that's not a good midpoint to check. I'll check this midpoint. In this midpoint, since we are less than it, we can reduce our range to just this, and that's how the binary search would work. But does this make sense? What does the orange line represent? The orange line represents the value of f that is given to us in the question. So for each mid, we are checking number of operations and comparing to f. Yes, exactly. Okay, so now say we were to do this just as is, like how would we actually do this binary search? How would we check this value if it's working or not? Well, we'd have to like go through the array. Oh wait, sorry. Yeah, we'd have to like wait, where is my example array? Yeah, it's here. So we'd have to go through the array, start an interval here, check till which element is deleted. Of course, we're gonna have to sort it beforehand. Then we're gonna have to run the upper bound function. Hopefully, people know what that is. That just gets the next greater element from 4, and we go to 10, right? And now from 10, we again do upper bound, and we get 16 after deleting. So we go here, right? And we keep doing this. So hopefully that makes sense. So what would the time complexity for one check be? Like to just check one value of k, what will like the time complexity be? Yeah, like binary search itself will multiply a log factor, right? But like this one check, yeah, it's I think you can do it in O of a plus n as well, actually, because you can pre-calculate for each value which is the next greater one. But if you just want to code it fast, you'll have a log factor here as well. So it's either n log n or n plus or O of n with O and O of a pre-processing, depending on how you do it. Basically, you can do this, right? If you can't, then I will explain exactly how to do this again. So please tell me. If not, then I can, continue with the next part. Oh yeah, if you manually try to get to the next element, that will not be fast enough, I'm pretty sure. Even this is not fast enough for the full solution. But the full solution has like a cool trick. Maybe if you code it right, coincidentally, it may pass the full one as well. Because it's not exactly an explicit thing that you do. But okay, did you guys understand how this part in particular works? I'm hoping to see. But the full approach is at n log n per query. If you saw it in the beginning, wouldn't O of n be faster? Actually, wait, hold on. I'm pretty sure you would still probably need to use upper bound to find the next element. Oh no, you don't. You don't need to. It wouldn't be O of n, it would be O of a. Because, well, basically you need to store some array like next of x is equal to the element that is bigger than x on sorting the array. But the full approach is at n log n per query. Yeah, per query it's n log n, and then when you add binary search, it will become another log. So you will have n log n into log of the range size, which is what's the max value of k? What is it k? Yeah, the max value of k is a again, so it would be n log a in total. So you don't need to care about the actual logs. It's like basically n log square. You can just think of it like that. So how many subtasks would this get? Hmm, I'm pretty sure this should probably get like these subtasks. Maybe not this one. Yeah, it probably wouldn't get this one. But I'm pretty confident it will get all of these. Seems like it would. So if we assume that, then we have 100 minus 8 minus 17, and now we're at 75 points. So we have 2 times the points. Not even 2 times. How many was there? 27. Oh no, we have around a little less, 2.7 times the points needed to qualify. So you already qualified. Or maybe some of you guys think that you wouldn't be able to come up with this in the contest and all, which is also fine, because when Samik covers P2, you'll see there's quite a lot of, like easy subtasks that you can get on that too. Okay, but now I'm gonna explain the final subtask here, which is the real cool subtask. But I just want to emphasize again that like even if you just got like this much and you got some stuff on P2, oh, just check the subtask. Yeah. If you got some stuff here and some stuff on PT, you would qualify even as a 12th grader male. Okay, now the full solution. So I kind of like this binary search approach. I feel like, it can be extended to full. It seems like this would probably be the intended solution. So now I'm just gonna think about anything I can do to optimize this, really. Okay. Is there anything that comes to mind? Because it's not a very obvious trick, but can DP be used in this? Yeah, I don't think it's feasible to use DP in this. At least I don't know of a solution with DP, personally. Anyway, is there anything that comes to mind in order to like optimize this? Any interesting observations? Okay, it's not actually that obvious, so I'll probably just say it. Uh, okay, wait. Instead of asking that, I can ask you guys: have you ever coded the sieve of Erasthenes? I think I pronounced that right. Actually, I probably didn't. Erasthenesis. Uh, Erato, Eratosthenes. Yeah. Have you ever coded that up? Yeah, it doesn't matter. I think everyone understood what I was talking about. So if you haven't heard of it, it's basically like it's an algorithm that finds the number of prime numbers less than or equal to x in now this is the cool part. If you guys haven't heard of it, it does it in O of n log n time, where n is the max number. Yeah, n log n if you do optimizations, but it's very easy to prove that it's n log n as well. So let's just say n log n. Like it finds it in n log n time. Now, why does this work? If you guys haven't seen the code for it, maybe I can try pulling it up. Save of Erasthenes. And probably see it here. Okay. Uh, so there's one linear loop and there's one loop that goes from I squared all the way to n, and it basically adds I on each iteration. Right. Okay, I think it's probably unreasonable to expect someone to come up with this. I'm thinking about whether I should say it or give you guys some time. But I think no, I think it is pretty unreasonable to come up with this. Okay. Uh, well, I can give some motivations. How many people here know some calculus? You don't need to know a lot. You just need to know like school level calculus actually. Probably even less than that. Okay, not less than that, but at Samik's cooking something up. I don't know. I said. Okay, 10th graders won't know. Hmm. Okay, so I don't know if you guys have heard of this or not. This result in calculus. That the integral of 1 over x is natural log x, right? If you have, then this entire part is going to be very trivial for you. If you haven't, then this is going to kind of look like magic. Yeah, like okay, so I don't know if you're confused about how it comes here, or yeah, I mean this is actually used in this problem, which is okay. That's pushing the boundaries a bit, but it's somewhat used in this problem, which is pretty cool. Samik, will you? I mean, we can help them out. I think. You can tell them all of the calculus sums they'll need to solve to clear INOI. You don't need to think of it. You just need to have seen it before. And if you haven't seen it before, that's actually pretty normal. You will definitely filter it. So, anyway, so if you're like, okay, what the hell did this guy just say? Then you can like prove it with like C++. You can just code something like you can code something like something like that, and you'll see that it grows really slowly. Okay, and in fact, you know what? You don't even need to prove that. You just need to prove that it's like slow enough that it's like not something big. I think it's gonna be like, okay, the idea is fine. What does it do here? Okay, great question. Okay, now, now this is gonna be a bit confusing to explain, I think, but I'm gonna try anyway. Okay, so what is the worst case gonna be? Worst case as in what is the case? Okay, wait, I'm gonna go to my whiteboard. Which is the case where I have the maximum number of operations that I need to perform. I get no concessions at all, so as to say. Why can I not draw lines? Okay, there you go. So this is small m. Uh, this is capital M. So let's say that every single element over here, like let's say this was, or I'll use blue maybe. This was m plus 1. This was m plus 2. This was m plus 3. Basically, I'm saying there's no gaps at all. Like the array is completely filled all the way. There's no gaps. You need to clear each and every element. Right. This is like when we'll need the maximum number of operations. Every other case will need less operations than this. Right. Okay, yeah, you don't need calculus still. You don't need to code up calculus, but that explains why this works. Don't worry, guys, it will become clear. That was just kind of like clickbait, so you guys would pay attention. I mean, not that it's false, but that was mostly just clickbait. Okay. Uh, but you guys realize that this will be the worst case, right? I haven't explained it yet, so it's completely normal to not get it. You can't get it before I explain it, right? I mean, no one here can read minds, I don't think. All I'm saying is, let's say I had another array like m. I didn't have m plus 1, I had m plus 2 in it. Let's say I had m plus 4, and it's the exact same other than that, but now there's just some holes. Then I am saying that this array is going to take less operations to clear out than this array. That makes sense, right? Less amount of elements to uh, like the less amount of elements we have, the less number of operations we will need to perform, like especially if one is a complete subset of the other, which is the case here, right? Now what I'm saying is, let's say that my interval size was k over here. Okay, then I would do one operation like this, which would be of size k. I would do one more operation over here, which would be of size k. I would do one more operation here, which would be of size k, and I would do one more operation here of size k. So I'm just going to define a variable called delta as capital M minus small m. Then we'll basically at max perform delta divided by k operations. Right. And you need to seal it, of course. This is the maximum number of operations we'll perform when we have an interval of size k, because we can just completely cover the interval constructively like this, and we will be done, guaranteed to clear every element, right? Does that make sense? Okay, does it like not make sense since Hmm. Look, I'm not saying anything deep. I'm just saying that, like, if you had M being the smallest and capital M being the biggest, and you just placed intervals directly, like, consecutively to each other, like, there's no gaps in between, like, an interval of size k here as well, and like you have intervals of size k everywhere. Like, if you completely span the range from small m to capital M, you're definitely going to clear it. Uh, Maybe I can give an example as well. Actually, let's say I had 1 to 10. Okay. Uh, 9, 10, and let's say k was equal to 2. Okay, then I would have operations like this: 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10. And you can see that we take 10 minus 1. Okay, actually, maybe it should have been plus 1 over here. Uh, m minus m plus 1. So we take 10 divided by 2 operations, which is 5, right? Because we have 1, 2, 3, 4, 5 operations. That's all I was saying before. Right. Delta divided by k number of operations. Yeah. Okay, so now does this make sense? Now, what I'm going to say is, like, let's say I'm doing this for 1k, it could be pretty messed up because if I take k is equal to 1, then I would perform n operations. If I take k as like something bigger though, like let's say I take k is equal to like 100 or something, I don't need to perform n by 100 operations. So let's say I wanted to do this for all the values of k, because that's kind of what we are doing in this problem, right? We want to try different values of k. So let's just say if I had done them for all of them, how much time would this actually take? So it would take, I'm just gonna write, instead of delta, I'm gonna write n, because, or I'll write m, okay, instead of delta. We'll take m by 1 plus m by 2 plus m by 3 plus dot 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 plus m divided by m number of operations, right? Now we can just factor out an m over here. We're gonna be left with 1 by 1 plus 1 by 2 plus 1 by m, right? So now this is where the integral comes in, because an integral sums up a lot of things in between this as well. It actually extends beyond m as well. So we can say that the integral's value is definitely going to be greater than or equal to our value. So I'm just going to write this because I wrote it in chat. I think I have to know. Or you can even put this at infinity. It doesn't matter. You know what? Let's just do infinity. Right, and now we know that this over here is natural log, right? No, this is natural log m, and m is obviously positive, so I'm not going to write the absolute value. And that is why this entire thing is m log m. So since we multiply that m from outside, the complexity of this is m log m. So now this actually sounds pretty absurd because I got a log factor from doing basically nothing. Or let's say I got a log factor from doing something that appears pretty natural. So you may be like, bro, you didn't even divide the range in half or something. So how did log come up? But it is actually true. And you guys can confirm it with code. There's probably a way to prove this without calculus as well, but I just don't know it. So now, how does this tie back to the original problem? Because I'm sure everyone's waiting for that, because I just explained a bunch of math stuff. Now we want to know how this actually solves the problem, right? So what we do basically is, instead of doing everything in the binary search itself, what we're going to do is we're going to loop over k is equal to 1, k is equal to 1, k is equal to 2, k is equal to 3, and we're going to do this all the way up to a, okay, which is the maximum value of the array. We'll loop all the way to k is equal to a. And now we're going to say we run this binary search loop looking thingy for each one of these values of k. And now you may be like, oh my god, but each iteration itself can take like n log n time. And we have these many k values. We have a k values. So isn't this going to be O of n into a log n time? Right. But the trick is to realize that every single time we do one of these like upper bound operations to move ahead, oops, yeah, we do one of these upper bound operations to like move ahead, we actually move ahead by a distance of k. Like it has to be that because of our interval itself is like size k, right? So how many times can you move ahead by a size of k when you only have a numbers? The answer is a divided by k, right? So each one of these is not going to take n time, it's going to take a divided by k time. So so the actual time complexity is going to be summation a divided by k log n. And you can, like I said, you can even get rid of the log n by pre-computation, but uh, yeah, you know what? Let's say we got rid of the log n by pre-computation, or even if you don't, then you're gonna have a log n. Now you'll be like, oh my god, this is literally the same thing as the previous solution. We had a log square there as well, so how is this going to work? Well, the key difference is realizing that we pre-computed this for each k, right? We're done. The pre-computation is done. We are going to have to do this in total one time. Okay, before we do anything else. After that, what we are going to do is we are going to just, where's my graph? Yeah, we're just going to run this binary search, but now we actually know this function. So I have written it in orange over here. No, I've not written in any color. So what this blue graph is over here, we're actually going to know this graph completely now. Like we have literally just pre-computed the graph in this much time, and you can get rid of this log n if you pay an additional linear factor over here. So now we literally just do a binary search over like the red lines to find the red line that's like furthest to the left that is less than or equal to f. And this will be log of a time per query. So the total time complexity would be like how many queries are there? The q queries. So it would be q into log a plus a log n, which is fast enough to pass. So that is the full solution. Hopefully, it wasn't too okay, bro. It's not. The log n thing is something you see once and you remember it. You don't need to derive it in the exam every time. But hopefully it should be intuitive that like it's not gonna be all the way to n square. Like that loop from interval sizes. As you increase the interval sizes, you know it's gonna be better than n square, right? Like significantly better than n square because this at the time we come up to like half the values, we're already doing like 2 times better than we were before. Like at the very beginning, and that continues. Okay, wait, hold on. I'll just check that after I'm finished with this. Uh, and we just continue doing that till the end. So, I mean, you can kind of like see that it's going to be log. By the way, like you didn't have to even get the log to like I said, like you could have not gotten any of this, just gotten all of this stuff. And let's say you're doing well, maybe you could get this stuff too. And you'd already be like 2.7 times above the cutoff. So like you're completely fine, you know. Um Okay, is this the same idea? If you can check, let's have a look. Hmm. Okay, we have an unordered map for a cache. Yup. Okay. Calc operations or calc operations. Yeah. So this cache is basically just like looping over all values of k in my equivalent. This calc ops is okay. So this is the only place where I think your thing may. Wait, no, but this does get AC. So let's have a look again. Last is equal to array I plus k, while I less than n, and array I less than or equal to last I plus plus. Samik, is this the same thing?
Yeah, because the reason why it works is harmonic sum.
But he's not
Look at
doing
the
the.
solve function.
But is he doing the binary search thing? I mean, the upper bound thing over here, or just like incrementing it directly?
Uh, I don't know that actually. Not sure.
That's the one thing I'm not sure about as well. If I were to say anything's different, it would probably be this. The harmonic thing is going to be the same because even though you don't explicitly invoke or prove it, it's going to be true, of course.
Hmm.
Yeah, you're supposed to sort for my solution too. Okay, so hopefully that makes sense. Do you want to like add something to this, Samik, by the way? If you thought that it was unjust of me to include calculus or something, if you want, feel free to, uh, like, yeah,
I don't think so.
a non-harmonic series solution. Is there one?
I don't think there is because you need to use the approximation to prove the complexity of this solution. Any solution, I think.
Min value, max value, if one, max value minus min value, count if one divided by I. Okay, so what you missed in this is something I discussed uh over here in the array thing. Let's say over here you have 1, 4, 10, 16. So what you're doing is you're completely spanning the interval, right? By the way, I think this should be ceil, even if you were, it should be f plus I minus 1 divided by I. But regardless of that, uh, you are completely spanning the interval, which is what I said over here. That's what you're doing now. But you realize that there can be gaps in between. Like you'll include this interval even though there are no elements in it, so you could have actually excluded it. That's the only thing wrong with your. But that's what you missed. Hopefully that made sense. Okay. Okay, so realistically, how many points do you guys think you would have gotten on P1? Okay, now I want you guys to be optimistic. Okay, I want you guys to think that, like, literally your best day. You're like rocking. You need to think that like, oh my god, I'm biased because like I knew the solution or something. 75. Okay, what about the others? Come on, I need to see values that are like 2 times about 27, guys. Come on, just like 75 again. Okay, got AC, but it took me 2 hours for the final. I think 20 to 30 points, which is already good, right? Any other people? Like, I actually want to know because, like, how you think of like how you perceive how many points you'll get also kind of matters, because then I also know which parts I explained understandably and which parts I got cooked in. 50 easily, 40 points. 80. That feels like they would get out the cutoff for two problems in one, which is a pretty good state to be in. Even if you do, you can say it, by the way, because you'll probably see that like. Okay, now what's like a mediocre case? Let's say not your best case, but like an expected case for how many points? 30 points, 40, 50. Okay, 60 with pressure, 30. Okay, then I think that's a good thing. Okay, so then I think even if you guys didn't even like, of course the full solve is really cool because it involves calculus. So I like it, but you don't need to do it, and you can just get 30 points and be happy and get to INOI, and it will be great. Okay, so now we're going to move on to P2, which Samik will explain. Uh, he's also obviously gonna go through all. How many subtasks were there? There were 10 subtasks here and 10 subtasks here. Yeah, so he's also gonna go through each subtask, and hopefully, I think he's planning to actually explain it in an easier way, and it will hopefully be a lot more straightforward to follow. If it's not, then at least that's what he told me before we started this meet. So, so yeah, we'll see if that's true. You guys can let me know if you think his explanation is easy or not. Is calculus better than parallel binary search? Oh my god. I was actually thinking of trying to use this a bit before you can ask Samik, but then we thought that it's actually a more advanced topic than the log amortization thingy. So we ended up just going with the straightforward solution. I'm not sure. I haven't verified if parallel binary search will work or not, so I can't say anything definitive. But yeah, the worst case is still not zero, which is kind of a W. Not gonna lie. Hmm.
Okay, should I start now?
Yes, go ahead. I'll
Okay,
stop
well,
sharing my
hello
screen.
everyone. Yeah. Okay, so before starting, I want to know how many of you guys actually gave this as a mock and how many of you just joined because we were doing a lecture. You please put a yes in the chat box along with your score, the one you got in the mock. And be truthful, okay? Okay, we have one person. Only two people. Okay, we have three. Guys, come on. If you gave the mock, tell me how much you got. Okay, cool. Cool. So I think most people are already scoring well above the you. Mm-hmm. Okay. Cool. Okay, so most people are scoring above the cutoff. That's pretty cool. So I hope my explanation is not gonna be too simple because I was planning on covering the simpler subtasks. But let's start. Okay. Is my screen visible? Okay. By the way, if anyone has any doubt, please feel free to unmute because I can't see the chat while I'm looking at the question or looking at the whiteboard. Okay, so it's the wrong problem. Yes. Yeah. So just to summarize the problem, you have uh, n students, right, who gave contests, two contests specifically, out of p points each, and now you have to select the best one, and you can use a weighted average for that if you guys know what that is. Do people here know what a weighted average is? Okay, well, you can use this formula. Let me zoom in a little. You can use this formula. A is the score the person got in problem contest one. R is the you can call the weightage, and then B is the score they got in the second problem. That's it. You just have to find for every single person, could they be the highest scorer for some value of R out of the n participants. Does that make sense? Like, does everyone know the problem and understand it? Okay, cool, cool. I want more interaction, by the way, guys. Please answer in the comment section, like not the comment section, the chat box. Right? Just don't stay and watch. Yeah, okay. So looking at the subtasks, I think the first subtask should be very, very obvious. Right? Think about it. If there's one student giving an exam, then obviously they're going to be the highest scorer, right? I don't even think I should need to I don't even think I should need to talk about this. Yeah. Yeah, actually P2, even though the full solve has like convex hull and stuff, it's actually the more scoring problem, I feel, because of subtask 4. I mean, it looks really long, but let's get to it after 2 and 3. Okay, so two subtasks. Subtask number 2, it's just when you have one person or two persons. Well, one person is obviously again trivial. Of course, they are gonna be the highest scorer. What about two? Do you guys know the solution for two? Like if two people give two exams and we have this weighted formula, how do you think it's gonna work? What do you mean by check 0 and 100? Yep, that is correct. That is correct. I mean, instead of saying R0, R100, you can actually just think about it this way. If, let's say, in exam 1, if person A scored more than person B, then we can just pick R to be 100 and they can win. Otherwise, we look at P2. There, if A scores greater, then again we can use by N. No. N is the number of people. We have two exams. That's very important. Yeah. Because otherwise you'll have some n-dimensional convex cell that'll get really complicated. So it's 2 dimensions, 2 exams. This subtask has 2 people though. So
Wait, Akash, did you misread the problem in the contest or something? I hope not.
yeah, I think. Oh, okay.
Oh my god, okay.
Oh no.
That's pretty unfortunate, but it happens to people, so it's okay.
Yeah. Okay, let me get to a whiteboard. So, okay, wait. Do people know n is equal to 2? Or do you not? Like, skipped reading. No, guys. You don't want to be doing that. Please read everything, all the information that's given. And the reason why subtask 4 is so important is because it's a very, very easy subtask. Because it literally tells you what to do. It is sufficient to consider only integer values of R. Like, it's literally telling you, just check all integer values of R and just check if your student can be the maximum. Like, that's it. You don't even need to think. Okay, first of all, do people understand n is equal to 2? Okay, cool. Because also this is like a general thing I'll say even in ZCO. If there are any sort of special cases, just look at them, because special cases are usually easier to solve. And they're gonna...
Also, so it's kind of counterintuitive, but the longer the subtask is, the higher probability that it's actually way easier than the original problem. Because that means that the constraints they've given you are some very weird constraints that are going to be very easy to solve.
Yeah, because remember these subtasks, they think before putting these subtasks. Like, there is an intended solution for almost every subtask. And again, as Avigna said, if it's a complex looking subtask, then it has some special solution. Because, I mean, problem setters aren't going to write a whole ass paragraph unless they have a solution that goes with it. Okay, so you guys understand these two. What about this one? So actually you don't even need this, right? If you do subtask 4, 1 and 2, you'll get 27 points, which is enough to qualify. You don't even need to do P1, you don't need to do anything else. Just n is equal to 1, n is equal to 2, and check all integer R. That's it. Like, it's legitimately that simple. Okay, ZCO is very, very simple. So, but let me cover subtask 3 as well. So, are there any people who don't know the solution to this? Minimum score, I would say you should probably score at least 0. A negative score wouldn't look good. You know, like, bro, imagine telling your parents, yeah, I scored -1 marks on ZCO. Like, that's not gonna look good. I mean, yeah, non-zero is also a good thing, but I mean, 0 is fine as well, in my opinion. Okay, Yep. So P2 this year, 2023 was really scoring. So, and again, this is all the more reason you should read everything, because P2 is supposed to be a little harder, but it was actually the more scoring problem. Yeah, you don't need to, right? You don't need to score 200 out of 200. Even if you score, like, say, 27, you're gonna qualify, right? A ZCO, I did not AK ZCO 2023. Okay, anyways, guys, back on point. Is there anyone who wants me to cover subtask 3? By the way, like, if you don't know the... Okay, well, let's cover it for Vigna. So, for all students, either A of I will be 1 or B of I will be 1. What does that mean? So, that means that if you think about it, there's two types of students. One type of student scored 1 marks on the first exam. The other one scored 1 marks on the second exam. Now, this is actually like just gonna be the check R is equal to 0, R is equal to 100 thing. Because all of the students that scored 1 on the first exam, out of them, whoever scored the highest on the second exam, like obviously he's the one who's gonna get picked. There are no corner cases, actually. Because there's no way someone who has less than you, like maybe equivalent in what do you mean by that? Yep. So this is, and actually maybe this will be clearer when I look at the full solution. And by the way, I'm not gonna cover the full solution in too much depth, right? I'm just gonna say that because it is CHT, and I don't think most people know CHT. But anyways, let's get to subtask number 4. This is again pretty simple. It tells you what to do, right? It literally tells you what to do. The statement tells you what to do. When A is only judged and when B is only... so that is R is equal to 0 and R is equal to 100. That's the simple kind of thing. But anyway, subtask 4. Do you guys understand that? Just consider all integer values of R and then calculate this formula, right? They gave you the formula for every single person and just check who scored the maximum. And you're going to be like, okay, yeah, so I can probably take this person. For each R, go through the formula. Yep. For each R, we want the max. Yep. All the maxes, right? Keep that in mind. All the maxes, as all of the people who scored the max, they all can be picked as the representative. Problem setters didn't frame the question that well. So, okay, so there's two things, right? There's two things here. First of all, you can't complain like that in the actual ZCO or INY, right? Like, no one's gonna listen to you. And secondly, it may be intended as well, because sometimes that's just what they want to do, right? They want to test your comprehension skills. Because I've legitimately seen OI problems which do have this kind of stuff. Not so much in Indian OI, but foreign, like what's it called? Foreign Olympiads, they have this a lot. Joy is pretty clean statements, I think. NOI as well. Okay, so, do you guys understand subtask 4? You loop through all the R's, you loop through all the participants, and you figure out their aggregate score. whoever scores the max, just mark them as, yeah, they could be the representative, this person could be the representative, this person could be the representative, and output it all in the end. Okay, so after this I'm gonna go straight to the full solve actually, because if I had to say, right, if you were doing this as a mock, the first 4 subtasks are what you should have gotten 100%, right? Like these subtasks, guys, you should not have missed these, okay? Like I'm just gonna put that out there. You should not have missed these, especially the first 2 and the 4th one, because 3 maybe you miss some very very edge case where there's no students who scored AI is equal to 1, maybe something like that. But the other 3 subtasks, guys, they are very trivial, right? You should have gotten them. Okay, now getting to the full solution. Okay, a misunderstanding. One thing that I usually do if I'm not sure I understand the problem properly is actually look at the samples, because every single problem will have samples, and usually 1 to 2 samples will have an explanation. So just read this, right? Just go through this and think about, does that align with what I think the problem is? If it does, then binary search for. Okay, well, anyways, getting to the full solution, let me open up a whiteboard here. So you have given A of I and B of I for each person, right? How much they scored in the first exam and how much they scored in the second exam. And now, this is like a general rule that I think of, but what does this look like, right? You have a pair of integers. What does this kind of look like? A pair of integers. A line. Yeah, that's a very, very good intuition, because we can think of it as a line and we can think of it as a point. Yup. A pair of integers. Yes, I think that's what I said. It is a pair of integers. Ordered pair. Line W. Yup. So the solution that I love is the one where we look at this as points. So we think of this as x comma y. So if I were to graph them, how would this actually look? This is x, this is y, and maybe this is person 1, this is person 2, this is person 3, this is person 4, and so on. Every single person is a point. Does that make sense? As R changes, B goes A. What do you mean by that? No, this is not going to be sweep line. This is going to be convexal. These points represent the scores. So the x-axis is A of I, the y-axis is B of I. Right, that's what I said. We have a pair of integers that kind of looks like a point. Yep. Okay, so now let's think about how the representative, what properties the representative has to satisfy. And maybe this is a little hard to just think of automatically, and especially if you've never seen stuff like this before. And it might be easier if you play around with this in Desmos, right? Like, I'm actually going to recommend that. You don't have Desmos and ZCO. I'm talking about, and again in ZCO, you probably wouldn't even get the CHT solution. What's
Which, Samik, by the way, I think the solution you're describing is like, we learned this thing called linear programming in 12th grade, where we like have points that we plot and we draw the polygon formed by them, and you check each of the corners in order to maximize a value. I think it's the same thing actually.
Yeah. Except
think
here
so,
we
yeah.
can just output all of the corners of the polygon. We don't even need to
Yeah.
worry about the math.
Yeah, because like um that this the proof for LPP is actually probably the same as what you're going to say, I think. The play around with Desmos thing.
Maybe. Okay,
Okay.
so what properties does this satisfy? So let us say I picked r to be some number, right? Like I picked the value of r. Then again, if I just write down the equation here, actually I'll write down the equation so it's easier. Here's the equation. AR plus B 100 minus R all over 100. Okay. AR. Also, I'm really sorry for the bad handwriting, but you're just gonna have to deal with it. Okay. So just right out the gate, because we are looking at the maximum, this divided by 100 doesn't really matter. Like I can just maximize this value, it will look the exact same because we don't have any negatives. Now if I were to expand this out, oh, by the way, let's just substitute in x and y. XR plus B 100 minus y r. Oh, this should be y, my bad. Now so if you look at this relation, right, and let's say you talked about what if the aggregate was k, some number k. Again, I'm just using this to show you how this is gonna look visually, right? Which is I hope everyone can just realize this is gonna be a line, by the way, at this point. Ekansh, it's actually the other way around. I'm the one using the tablet. Avigna was drawing with a trackpad. Okay, wait, do you guys realize this is gonna be a line? Yep. So if I look at this, for some r, it's gonna look a little like this. So this value is maybe 10, this sums up to 9, this sums up to 8, this sums up to 7, this sums up to 6. Kind of realize what that means for any particular r? Come on guys, say yes or no, because this is a little mathy. I want to make sure everyone is following. Can you repeat that? Yeah. So so let's say I set r to be something. Let's say I set r to be 1, or let's take 50 actually, because that's pretty easy to draw. Then every single point on this line would sum up to something, say 10. Then on this line it would sum up to 9. On this line it would sum up to 8, and so on. It's sort of like a gradient. Yep. And another observation, just a quick observation here actually, is r is equal to 0 represents this, and this line, r 0 and 100 represent a vertical and horizontal line. Is gradient a big hint for CHT? Actually, no. This gradient thing looks a little similar to linear programming, as Avigna said, less than CHT. Different, yeah, they would not be. Because R is changing the slope, so it's going to change the angle. So now that you have seen this sort of line analogy, one last visualization I would like to make is, let's say I set r to be some number and I have this line, right? Then how do I figure out the participants that are gonna have the max score with this r? I can just, move this line towards the left until it hits a point, and I can say, okay, that's the maximum. If that makes sense. Again, this is just a visualization because this is the part that I feel like will actually help in discovering that this is CHT. Okay, sure. So I said that all of these lines have some sum, right? So let's say this sums up to 10, this sums up to 9, this sums up to 8. Then that also means what I could just do is I could take some line which sums up to a really high number and then move it parallelly, right? So, okay, let me try to draw a better visualization. So if this sums up to 10, this sums up to 11, then this sums up to 10. So similarly, we just keep on moving this line to this direction until it hits a point, and then we can, this would decrease, because we are going from the highest possible value to the lowest until we encounter some student who actually reached that score. So if I had to give like an analogy for this, it would be, say you wanted to find out the highest scorer in your class in your math final. So you can just ask everyone, did anyone score 100? Did anyone score 99? Did anyone score 98? And you keep doing this until 0. And yes, boundary, that's sort of, hinting towards CHT now. Because CHT also looks a little bit like building a boundary around points. And okay, now this is just going to be something that I can't really prove. It's just what it is. But realize this. Let's say I took a softboard and I put these dots into it as pins. Like I took a square softboard and I put in these pins into it at exactly these positions. Then I could just like use a string, hold it out, stretch it out and move it towards that direction. Just see which one it hits first, right? I'm sorry if it is getting too physical, but this is a good analogy, I feel like, for CHT. Outer boundary, yep. So this thread thing is actually what CHT does as well. So, okay, another physical analogy for this would be, what if I took a really big rubber band, right? And I stretched it out, right? I stretched it out this much and then I let go. Then it would form some structure. Yeah. So this is where the convex hull comes in. So first of all, can you see why this rubber band will actually only touch the points where it's like a student representative, where it's like a kind of corner, if you think about it. So actually this rubber band thing is what a convex hull is. So if you take a piece of board and if you put some pins into it, and then you take a rubber band, you spread it across and then you let go, whatever points the rubber band touches, those points are said to be on the convex hull of it. Like that's literally what convex hull is, a rubber band around some points. And that's what we have here as well. And R is like other dimension. No, so this is where we completely removed R. because a rubber band is soft, right? Yeah, but since now we're using a convex hull, it is like a rubber band, it is simultaneously checking for all angles. Let me try to do like a visualization again. So let's say these were our points. Now if we start with this line, we move it over here and we touch this point. We start with this line, we move it over here and we touch this point. We start with this line, we move it over here and we touch this point, right? Now think about what a rubber band would do. If I started out with this and if I just let go, like it would immediately go around these exact points. And again, that's just how a rubber band works. Like I don't know the physics behind it, right? Like I don't know elasticity or anything. So please don't ask me why that is. I just know that is how it is. Okay, so now that you guys get the rubber band analogy, again, the rubber band is a convex hull. Like that's literally a way to define the convex hull. Like you take some points, you put a rubber band around them, whichever points they touch, that's the convex hull. It's literally the definition. So now you just use the formula for finding out the shortest perimeter containing all points. I think that may work. Actually, I'm not completely sure. Yeah. It's not gonna be the area because for the area you can pinch it and you can get a curve, and that'll be better. I think the perimeter thing is correct because probably that's what elastics do, right? They try to minimize the, what's it called, length. Okay, well, anyways, so now you can just use, oh yeah, just one quick thing that I want to cover here. Let's say there was a point over here as well, then the rubber band would go around it as well, right? But you have to remember, for this, we can't have a line that goes from these directions, right? So what you want to do is you want to find the convex hull, and then you want to look at the top leftmost point and the bottom rightmost point, and you want to just go in this direction, look at all the points, and those are all the answers. That's it. It's not simple, but it is pretty cool in my opinion. Now for people interested, you can actually do this using the convex hull trick as well. So the convex hull trick is the same idea, but with lines, and you can't use physics in that, I think. So there's no physical analogy I have for it. Do you guys want me to cover the line solution as well? Again, I'm not gonna cover how CHT works. I'm just gonna 4 strings. No, a convex hull can have as many strings as possible because it's a rubber band, right? It's soft. Like that is the reason why we used a rubber band. I have the implementation. It does not look terrible actually. It depends upon the formula you use, because you can use geometry, which is gonna be like not good looking at all, and honestly that's gonna be a pain in the butt as well. Okay, how do you code it? Also, I'll just cover it. I'll cover the line solution in like 2 minutes. So the way you code it is there's some algorithm, I forgot what it's called, where they can generate the upper hull and the bottom hull, and then gram scan. So you can use that. And again, bro, don't try to derive that on your own, right? Like I'm just read on it. And also I'm not gonna explain it because it's a standard algorithm. Please learn it on your own. Okay, now getting to the line solution. So the line solution kind of flips this. So what did we do before? We substituted in x and y for a and b, and we set r and k to be some constant, right? Okay, so now we just flip the script. So instead of going for AR, let me just rewrite it. Yeah, plus B 100 minus R is equal to K. We can say AX plus B 100 minus X is equal to Y. Again, it's another line, but this time we'll have one line for each point. So n points, or say n participants, n lines. Let me add another page. Okay. And what will this actually look like? And by the way, remember x is r. So if I were to graph this, this would look something like this, right? A bunch of lines where y is the aggregate score and x is the r, and every single line represents a participant. Again, I'm sorry if this is getting too mathy, but this problem is it just uses math. Like you can't really escape math. Is this part clear? How I graph this? Not a lot actually, because I remember the post-contest discussion in this year was basically everyone was like, what's P2? So don't expect to full solve this in contest. Okay, so now R can range from 0 to, say this was 100, right? You don't know linear programming. I don't think that'll make a difference. Like this is just a one-off problem where this gradient thing, this string thing, this rubber band thing made sense, because I've never actually used that analogy in any other problem. Class 10, I think you're gonna learn it next year, so don't worry. And again, you don't need to know about it. CBSE has linear programming in class. No, oh wait, it doesn't. Actually, I don't know.
At least for ISC, it is class 12. Not sure about CBSE.
Even I'm not sure actually. Oh, maybe. I did maths quite a while ago, so I don't remember. Okay, so let's think about what the best, what do you call, the best participant has to look like. He has to have the highest line at that particular R, right? So wait, if I full this participant would be good for up to this value of R, and then this participant would be the best, if that makes sense. Yep, so now this again is a standard problem. It's called the convex hull trick. Again, you're just gonna have to read up on this. Like as long as you understand what we are looking for is the line which has the highest y value, right? Because the highest aggregate score, that's the person who'll get picked. So we just look at the highest aggregate score for each R. No, CHT is actually very simple to implement. It is very, very clean. Yep, because it doesn't use geometry. Oh my god, bro, if you can't get anything, then please just Google it. CHT, yeah, you don't need to worry about CHT too much right now. Like, CHT is a very advanced topic, right? Like, I'm legitimately gonna say most of you are not gonna be able to learn CHT before INOI up to a good level. CHT can be used for 1D DP. CHT is an optimization for transitions, not dimensions. Actually, I think the best applications of CHT are in 1D DP, because 2D you usually have like divide and conquer,